So here we have the exam, Differential Equations, Exam 1 from Fall 2024. What a year! What a vintage! Let's do this! Woo! Okay, now remember, always start by putting your name. If we don't put our name, we won't get the credit. And we're after all the points. All the points. All right, number 1. Find the general solution of the following equations. So we have A, B. Notice these are both first-order differential equations. Okay, so let's look at this one. Now, when we look, we see a y prime and a y, and it's in a nice form. So this is a linear first-order equation, and we can do integrating factors here. Okay, so good news is, what's in front of the y prime? It's not an a, that's question A. It's a 1. So we say, aha, how do integrating factors work? We take this coefficient, say, all right, the minus 4 over x, and we're going to integrate that. So integral of minus 4 over x dx, and that's minus 4 log x, which is log x to the negative 4 power. Or, if you like, that's log of 1 over x to the 4th. Now, we're going to take that term, and remember, for integrating factors, you don't just integrate it, you take e to that. So we have e to that. And e to the log, very clean. And so we get 1 over x to the 4th. Okay, so that's our integrating factor. What does that mean? Well, it means what we're going to do is we're going to take our original differential equation, and we're now going to multiply everything by 1 over x to the 4th. So we say, all right, what does that give us? Well, it gives us 1 over x to the 4th minus 4 over, and then there's a y there, don't forget the y prime, 4 over x to the 5th, y is equal to, here, we're going to get an x canceling, so we're going to get a 3 over x cubed minus 2 over x to the 4th, which we can write that as 3x to the minus 3, and minus 2x to the minus 4. Now, here's the magic of our integrating factor. You see this left-hand side, always, if we've done our job right. And of course, we're going to do it right. It doesn't hurt to check. But always, it's going to have a very specific form. Namely, it's going to be a derivative of something. And why do we want that? Well, because it turns out derivatives are easy to integrate. That's the whole plan. So it's our integrating factor, this part, times y. And of course, you can just check, take the product rule, and first times the root of the second, and then the second, and the root of the first. That works out. All right, so we have the derivative of 1 over x to the 4th y is equal to 3x to the negative 3 minus 2x to the negative 4. All right, good, good. Now, we're almost there. What's left? Well, we have to integrate. All right, no worries. We can do that. We integrate both sides. And we say, all right, what comes out? Well, the derivative of an integral is what we started with. So we say, okay, we have the following. 1 over x to the 4th times y, okay, equals, and now we just follow the rules. Add 1 to the exponent, and that would be negative 2 divided by negative 2. So we get negative 3 over 2, x to negative 2. Add 1 to the exponent, negative 3, divide by negative 3. So plus 2/3 x to the negative 3, and don't forget a plus c. And finally, we're almost there, get y by itself. So we get y is equal to minus 3/2, and we're multiplying everything by x to the 4th, so x to the 4th times x minus 2, x squared. 2/3 x minus 3 times x to the 4th, x, and then some constant, x to the 4th. And there we go. Part A, done. All right, part B. Y prime is y squared over 1 plus x squared. All right, now notice it's not linear, so that's squared. And it's first order, so you start thinking, well, there's only a few things I can do. And when I say few, there's 3. And we've already done one of them, linear first order. They're separable, and there's exact. Well, this looks separable. See how you have the y's and x's are separate top and bottom? So we say, aha, let's separate. So we say, okay, we're going to think of this y prime dy over dx, y squared over 1 plus x squared. Move stuff around. And so we'll move the dx across, move the y squared across, and then if you do that, then this becomes y to the minus 2 dy is equal to 1 over 1 plus x squared dx. And so step 1, separate. It's in the name of separable differential equations. Now that you've separated, the next thing is to integrate it. So we say, okay, integrate both sides. What's the integral of y to the minus 2? Well, the answer is minus y to the minus 1, right? You add 1, and then you divide by a minus. And, okay, which equals 1 over 1 plus x squared. Ah, beautiful. A work of art. It's arctangent. And then, of course, don't forget your plus c. Now, I like to go ahead and solve for y. So I'll move the minus across. So we could say, okay, 1 over y is equal to minus arctangent of x plus c. And then finally, flip it. So we say, aha, y is equal to 1 over, and I'll just put the c first. C, some constant minus arctangent of x. All right, good. And there we go, right? And that's the solution, yes? Yes? Technically, yes, and you would get full points for that. However, there's actually a fun little twist to this, which is that in this case, this doesn't capture all solutions. You might say, well, wait, what? What? Well, it won't capture constant solutions, and you'll notice if the derivative is 0, because derivative of constants are 0, y equals 0 is a constant. So technically, there's two sets of solutions. 1 over c minus arctangent of x, or 0. So these are the two possibilities. And so I probably shouldn't use that notation. We'll say equals y equals y. This is the full solution. But don't worry, if you didn't write down this y equals 0, you'd still get the points. They're testing you on the separable process and not on fine details. All right, number 2. Find the general solution to y double prime minus 3y prime plus 2y equals tan e to the t. Oh, okay. Now, notice what do you have? This part right here is not 0. It's non-homogeneous. But that's okay. We can still work with this. So there's a game plan. When you have constant coefficients, linear, and you say, okay, great. What we'll do is we're going to do a process. And we're going to first off say, ignore this tan e to the t. In other words, solve the homogeneous problem. Okay, so here we go. We're solving the homogeneous part. And when we do that, and we always do the homogeneous part first, we say, okay, well, that's y double prime minus 3y prime plus 2y equals 0. Turn it into an algebra problem. Because we love algebra. We're really good at it. And so what we do is we're going to have this new thing called r, and the derivatives tells us powers. Second derivative, r squared. First derivative, r. No derivatives, it's like r to the 0, so it's a constant. Set it equal to 0, and now solve it like you would algebra. And if you've lived a good life, and you have nice teachers, and of course you have nice teachers, they love you. They want you to succeed. They'll give you something that factors. Worst case scenario, throw into the quadratic formula. And we say, our roots are 1 and 2. Now, these are the solutions to the algebra problem. We're going to take that and turn them into solutions to the differential equation problem. Namely, what we're really doing, what the secret is we're thinking of, things that look like e to the r something. Now, here our variable is t, so we're going to use t's, not x's, but e to the r something. So here we say, the homogeneous solution would be some constant e to the t and some constant e to the 2t. So the 1 and the 2 are the coefficients upstairs. All right, that's the homogeneous part. And now we say, okay, let's look at the non-homogeneous part. Now the good thing about the non-homogeneous part is it's a relatively nice function. It's the kind of function that we often see showing up. And we say, okay, when it's the kind of function we often see showing up in these types of problems, we're going to use the method of undetermined coefficients. Because there's two approaches, undetermined coefficients and variation parameters. And variation parameters we don't want to do because it's a lot of work. The good news is they give us a formula for it, but if we can use undetermined coefficients, we do. Okay, so here's our thought process. We say, okay, our non-homogeneous part should be e to the t. So we say, okay, so what would we guess? Well, what we'd start by saying is, let's guess our particular solution to handle the non-homogeneous part. And we're going to say, well, we probably would guess something like e to the t. Now, the problem with that particular guess is it says, hey, wait a second. That e to the t, that already showed up. That's part of our homogeneous solution. So we can't use it again. Because if we try to throw it into the system, it would just say, whoa, it disappeared. And it's not going to work. So what are we going to do? We're going to bump it up. Bump it up. That's right. Bump it up. Why do we bump? We're going to add a t in here. Whoa. Okay. So we're going to add a t. Now, it won't vanish, and things will work out nicely. However, we're missing one more part. This is the method of undetermined coefficients, so we need to have an undetermined coefficient. So we'll throw something in front. Let's throw in an a. So our goal says find a. Okay, so how do we do it? Well, we're going to throw this into the machinery. And we're going to say, throw this into that differential equation and see what does a have to be in order for this to make sense. So we need to take a derivative and a second derivative. Okay, so let's take one derivative, product rule. So yp prime, that would be a e to the t. So derivative of the first times the second plus a t e to the t. And the first times the derivative of the second. And the derivative of e to the t is e to the t. Sometimes we take the derivative of e to the t and like, wait, did we really take a derivative? Yes, because we're following the rules. We're going to get our points. And okay, now second derivative. All right, derivative of e to the t, e to the t. Wow, they give us nice functions to work with. Product rule again. Derivative of t is 1, so it's a e to the t plus a t. Derivative of e to the t is e to the t. Or we can write that as 2a e to the t plus a t e to the t. Okay, so here we go. We're putting this into there. All right, so when we do that, what's going to happen? Well, we're going to say that 10 e to the t is equal to yp double prime minus 3yp prime plus 2yp. All right, and now we're going to replace each one of those with what we have here. And we say, okay, so that's 2a e to the t plus a times t e to the t. That's our yp double prime minus 3yp prime a e to the t plus a times t e to the t plus 2 times yp a t e to the t. Cool. Now, you might get nervous and be like, oh no, there's a t e to the t in here. But if we do our job right, everything's going to cancel, yes? And if they don't cancel, we didn't do our job right. So let's make sure everything's canceling. For the t e to the t's, we have one of them here. We have minus 3 of them here. We have 2 of them here. So if we combine these together, we get 0. They all cancel out. Beautiful. Now, we have to look at the e to the t terms. That's what we really care about. Well, what do we have? We have 2 of them here and minus 3 of them here. So if we combine those together, we say, well, that makes a minus a e to the t, 2a minus 3a. And that's supposed to equal 10 e to the t. And now we do our great match coefficients up. And we say, oh, that tells us that a should be negative 10. So our particular solution is minus 10 t e to the t. And now our final solution, if we think about what we did up here, when we wrote down y, we really should have been a little bit more careful and said, this is y of the homogeneous part. And now, so the general solution, right, because it said, find the general solution, not find a particular solution, but find them all. So what you do is you add those two pieces together. And so you say, okay, so the homogeneous part, c e to the t plus d e to the 2t, arbitrary constants. And then for the particular part, we have minus 10 t e to the t. And there we go. We're done with number 2. On to number 3. Find an implicit solution for the following differential equation which crosses the point xy equals 0, 1. All right, now this is a first order differential equation, and it looks hopeless. Look at all these things. Y e to the xy 2. But there's hope. And in fact, the way that it's written here, it's written so we should be like, aha, this is exact. We see it's of the form something dx plus something dy. And now we're like, oh, this should be relatively straightforward. So the idea here, if we phrase it in terms of multivariable calculus, is this should be the derivative of something with respect to x, and this should be the derivative of something with respect to y. Our goal is, what's that something? And as soon as we figure that out, life is good. So the process is pretty quick. What we do is we say, all right, we're going to take this stuff in front of the dx, and we're going to integrate. So we have integral 2x plus y e to the xy dx. So x is the part that can vary. Treat x like a variable. Treat y like a constant. Integral of 2x, x squared. Integral of y e to the xy. Well, y is a constant. So when we integrate e to the xy, it'd be e to the xy divided by the y. The y's cancel, so you get plus e to the xy. And then plus some function that is constant with respect to x, so it could be a function of y. All right, now we're going to do the same thing with the dy term. Integral of x e to the xy plus 1 dy. Okay, here, y is what can change. We're treating x like constant, so it's constant, e to constant times y. Well, e to the xy will be e to the xy divided by what's the constant part, which is the x. The x's cancel, so you get e to the xy. Integral of 1 with respect to y is y plus something which is constant with respect to y, so it's something which depends on x. And now our great stitching together. We say, what are the pieces that overlap, involve both x and y? Those need to be consistent. If they're not consistent, hopeless. Well, we have the e to the xy and the e to the xy. They match, so that's a part of our answer. Then we say, grab things which only have x. All right, no worries. This only has x. So that's part of our answer. Grab things that only have y. Well, okay, yeah, this only has y, and so that's part of our answer. Say, perfect. This is the f that we were after. We've accounted for everything, made sure the overlap agreed. Now, this is not the solution yet. This is your f, and it's not a function because we don't have an equals. So we put an equals, and we equal it to some constant. Oh, I've already used c and d. We'll put a. There we go. Equals a. And a, here, this is a constant. Now, if we were after the general solution, we'd be done. But we're not. We're after a particular solution. We're told we have to pass through the point x, y equals 0, 1. So we're going to plug in x equals 0 and y equals 1. So when we do that, we say, okay, we get 0 squared plus e to the 0, which is 1, plus 1 equals a. So that tells us that a equals 2. So our final answer is x squared plus e to the xy plus y equals 2. Nice! Woohoo! Yeah! We did it! We solved our problem On to number 4. Using a suitable substitution, solve the following initial value problem. You need not solve it for y. Okay, so it says that once we get something where we don't have derivatives, life is good. I suspect that's telling us things are going to get a little messy. All right, do we have a clue? Yes, we have a big clue. First off, there's a y there and a y there. That tells us it's not linear first order, and it's not in the right form for exact. But do you notice what we have upstairs? It's kind of small. It may not even show up on the screen, but I'll tell you what it says. It says y over x. So you say, I see y over x. And indeed, we can rewrite this as dy over dx equals y over x plus, here the x's cancel, e to the y over x. Now, good news. Whenever you see something where you say, I can rewrite it so everything looks like y over x, there's a way to approach it. And so this has a name, and unfortunately it sounds like we're repeating ourselves, but this is a homogeneous. And what we can do is we can solve it by a really nice substitution, and the substitution is y over x. Now, if you think about it, it doesn't seem that strange, because in some sense, what's the goal of substitution? You're like, well, what's on the inside? And you're like, well, oh, this y over x is on the inside. And so it's like, hey, that kind of feels like a natural substitution if you were channeling your inner calculus student. And shouldn't you be channeling your inner calculus student? Isn't that differential equations? Yeah, so we should. Okay, so anyways, back to our story. So we're going to set u equal y over x. Now, we need to figure out what dy dx is. So here, we're going to do a little bit of rewriting. That says y is equal to x times u. And so we can say, look, dy dx is product rule, the derivative of the first, 1 times the second, so that's the u, plus the first times the derivative of the second. And derivative of u is the derivative of u prime. Aha! Okay, all right, so now that we have our pieces, we're going to stitch it together. So we say dy dx, that's going to become u plus xu prime. And that's going to equal y over x, u. And then e to the y over x, e to the u. And oh my goodness, they already made it nice for us. Do you see that? We have the u's, and the u's are going to cancel. It's almost like they want us to succeed. And we say, what do we have? It looks separable. It will always be separable. When you do a homogeneous in the substitution y over x, if it's possible, it will always turn into a separable differential equation. Okay, so let's write that in the separable form. So we have x du over dx is equal to e to the u. So we're going to move the e to the u term across. We're going to move the x and the dx across. And if we do that, okay, lots of things moving around, we get e to the minus u du is equal to 1 over x dx. There we go. Now, we're ready. We've separated. After separation comes integration. Okay, good. Well, what's the integral of e to the minus u? It is minus e to the minus u. And what's the integral of 1 over x? It's log x. Throw in a constant. And now, are we done? No. What needs to be left? Got to put it back into terms of y. So we replace all our u's. All our u's being one of our u's. So this becomes minus e to the minus y over x is equal to natural log of x plus c. Do we need to do anything? No, right? It says you need not solve it for y, and so we can stop. We got rid of the derivative, and we put it back in terms of y and x. Life is good. Life is wonderful. So that means we can go to number 5. Consider the following autonomous differential equation. Here, autonomous just means, hey, there's no t's. It's all y's. All right, now, part A. Find the critical points, draw the phase diagram, and Then classify each critical point. Whew, okay. Well, let's do all of those things. Now, we do what? Well, channel your inner Calc 1 student. If you were a Calc 1 student and you heard critical points, what would you think? Well, you'd probably say, critical points, that's when the derivative equals 0, right? Yes! It's exactly that! Do it again! So when we're talking critical points, set the derivative equal to 0. Okay, so we say, all right, so for part A, we're going to set 0 equals 5y squared. And notice that y squared minus 4 can factor as y minus 2, y plus 2. And now we solve for when is this 0? And we just say, well, we get some zeros here at y equals 0, at y equals 2, and at y equals minus 2. So here are our critical points. Our y equals 0 to minus 2. Okay, so that's part of our answer because it says find the critical points. Now, draw the phase diagram. Okay, so for our phase diagram, we're just going to draw a line. Whoop! See, that's a pretty good line. And we're going to mark our points 0, minus 2, plus 2. And now what we need to do is, again, channel your inner Calc 1 and say, think about the derivative. And all right, so we're going to test, pick values here. So pick a big value, like a large number, like 3. You could pick 1,000,000, but just need something bigger than 2. And you say, okay, 5 times 9 times 5. Don't worry about the value. Worry about the sign. We saw the sign, and it opened up our eyes. We saw the sign. It's positive. 1, that's between 0 and 2. 5 times 1 times minus 3. Oh, dear, that means we're negative. All right, minus 1. 5 times 1 times negative 3. Still negative. Okay, plug in negative 3. 5 times 9 times 5. Positive. All right, are you positive? Yes, we are. Now, what does all that translate into? Where we see y prime positive, that means what? It means y is going up. It's getting bigger. Now, when we're on a line, bigger is to the right, and smaller is to the left. So we have to know our orientation. Okay, so bigger says we're going up. So we're going up. Smaller says we're going down. And we're going down. All right. Now, what do we have? Well, we have to ask the questions, what's happening at each point? Now, we look at the arrows. So for negative 2, the arrows are coming in. So negative 2 is stable. That means if you start near negative 2, you're going to move to negative 2. Now, what about 2 on the other end? Here, the arrows are pointing out. What does that mean? That means if you're not exactly at 2, if you're just barely off 2, you're going to move away. So this is what we would call unstable. All right. Now, what about 0? 0, notice the arrows are both pointing in the same direction. Now, it doesn't matter that they're both pointing that way. They could both be pointing the other direction. But if they're both pointing in, say, to the right, or both pointing to the left, means semi-stable. All right, so semi-stable. And that's our classification. So there we go. All right, good. We drew the phase diagram. We classified. So classification comes from looking at your phase diagram. Look at the arrows. Look at the direction. Now, part B. Given that y of 0 equals 1, determine the limit as time goes to infinity, y of t. Now, don't focus on the 0. Focus on the 1. It says, where are we? Well, it says we are at 1. There, that's 1. Follow the arrow. The arrow says we go to 0. That's it, right? As soon as you know your initial y value, you say, where does it fit in the line? And you figure it, and then you say, follow the direction of the arrow till you get to your next point. Or if it could be, say, if I start here, I might follow the arrow, then it would be off to infinity. And so, but for us, We're at 1. The arrow says go down. So we go until we hit our critical point. And so our answer for part B is that the limit as t goes to infinity of y of t equals 0. All right. And that's the answer. And, well, they didn't ask for justification, but if they ask for justification, just sort of say, no, this is where we start. We move to the left until we hit the point 0. All right. Cool, cool, cool. Oh my gosh. It's our last problem. And it feels like we'd only just begun to solve. All right, let's finish it. Let's finish strong. If we were taking this as a test, we'd still have 45 minutes left. But let's not take 45 minutes. Let's do what we need to do. Call it a day. All right. Consider the following third-order linear differential equation with constant coefficients. In other words, nice. Find 3 solutions to the equation. Okay. Now, interesting. All right. Well, part A. Find 3 solutions. Well, we have the third derivative minus 2y second derivative plus y prime equals 0. And, okay, well, what can we do? Well, we can turn this into an algebra problem. R cubed minus 2r squared plus r equals 0. Right? So the power corresponds to the derivative. And now we say, well, let's factor. R squared minus 2r plus 1 equals 0 because there's a common factor of r. And that last part factors as r minus 1 squared. We say, oh, nice. So our roots are 0, and then we have a repeated root of 1. Okay, so idea. Let's turn our roots into solutions. So, okay, we have our solutions. We'll call them y1. For the root of 0, we can just say that's 1. y2, well, for the root of 1, that would be e to the x. And y3, it's a repeated root, so we're not just going to use e to the x again. We're going to bump it up, bump it up, yeah. All right, x, e to the x. Okay, so here we have 3 solutions. Beautiful, 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 beautiful. Now, part B. Part B. Well, let's take a look. Compute the Wronskian. Are the solutions linearly independent? Okay, so for part B. Now, what's the Wronskian? Well, what we're going to do is we're going to take derivatives. And we're going to take a bunch of derivatives. And we say, okay, we start by taking the functions, and we're going to make a matrix. Okay, so here's the Wronskian. So we're going to take 1, e to the x e to the x. Now, that's the function. And then derivatives. Derivative of 1 is 0. Derivative of e to the x is e to the x. And product rule, derivative of x e to the x is 1 times e to the x plus x e to the x. Okay, so there's the derivatives. All right, that's the next row. So what's going to happen is every time we go down a row, we're going to keep taking derivative. Derivative of 0 is still 0. Derivative of e to the x is still e to the x. And then we say, okay, here, if we take our derivative again, we'll get e to the x plus e to the x plus x e to the x. Okay, that's our second derivative. You say, all right, so that's our matrix. Now, really, we don't just want to stop there. Now we need to take the determinant. Okay, so we're going to take the determinant. Okay, well, let's catch our breath and remember that we still have like 45 minutes, so that's plenty of time. And, all right, 1 times e to the x, and then here this will be 2 e to the x plus x e to the x. All right, so I'm doing diagonals. Then it'll be e to the x times e to the x plus x e to the x plus 0. Oh, that's nice. And then here we'll have x e to the x, wrap around times 0 times e to the x. Oh, also nice. Okay, now how about going uphill? 0 times e to the x times x e to the x. Oh, 0. Oh, I like you, column 1. You're my favorite column. All right, how about this column? E to the x plus x e to the x and 1. Okay, that's something. So minus, because we're going up, e to the x times e to the x plus x e to the x times 1. Okay, and then this last one, this 2e to the x plus x e to the x times 0 times e to the x. Ah, 0. You're doing the Lord's work. All right, so what do we have? Well, we have 2e to the 2x plus x e to the 2x. That's if we multiply through here. Minus e to the 2x and minus x e to the 2x. And, those cancel. And so we're left with e to the 2x. So that's the Wronskian. Now, there's a question. Are the solutions linearly independent? Well, the question comes down to what's happening to e to the 2x. Is it 0? Is it not 0? And the answer is e to the 2x is a not 0 thing. It's never 0. And so, since e to the 2x is not 0, then these are linearly independent. And there we go. Now, we're done. But before we do our farewells for each other, I just want to point out one thing. When they gave this test, there was a cool answer somebody gave, which had to be given full points because it was a correct answer. So someone said, hey, look at this differential equation. It says find 3 solutions. So they said, well, because everything has derivatives, what we can do is we can just say, I'll make my 3 solutions are 1, 2, 3. Now you might say, wait a second. Those aren't the 3 solutions. But notice it just said 3 solutions. It never said they had to be linearly independent. And then it says, well, what about part B? Computing the Wronskian. Well, the Wronskian becomes 1, 2, 3, 0, 0, 0, 0, 0, 0. And then you take the determinant of that, and you get 0. And it says, are these linearly dependent? And the answer is not linearly independent. And lo and behold, like I said, it's not what was intended, but it answered the question. And so they had to give them full points. Now, I am not encouraging you to do that. I am hoping that when they wrote the test this time, they're like, we're not going to be fooled again. But read the question carefully, and but don't try to like be clever. Just follow what they're asking, because that's what they'll look for. All right, we made it to the end. I hope you followed along. I know we went quickly, but this shows you'll have plenty of time. Plenty of time. You can do this. You can do well. You can do great. And let's get through this class. Let's move on and have a wonderful time. I believe in you. Good luck. And let's see each other again. Bye.